All right, everyone, welcome to the problems for this chapter. In this video, I want to show problems 1 and 2 of section A. And so let's get into it. Let's get started. Our first problem is to show that a specific field is the root field of a specific polynomial. Let me copy that down. So the polynomial that we have is x squared minus 2x minus 2 times x squared plus 1. And the question tells us that the root field should be q adjoin square root of 3 and I. Let me just make sure that's correct. Yep, that's what Pinter says. And so I want to see that this is the case. Now, for this problem, this polynomial is reducible because it's already explicitly factored. And so I don't need to worry about trying to factorize it further. I just need to know what sort of stuff the roots have that may not already be in the field Q. So I should probably start by finding the roots over some field extension, namely R, perhaps, just with the quadratic formula. So for this first term, at least I could use R. This one, I'll need to use something bigger. Maybe, for example, this will be where the I comes from, with complex numbers. The quadratic formula gives me positive 2 plus or minus the square root of 4 minus 4 times 1 times minus 2 over 2, which is 2 plus or minus 4 plus 8 divided by 2, or 2 plus or minus square root of 12 over 2, and I can see that that is 2 square root of 3 over 2. And so therefore we get 1 plus or minus the square root of 3. All right, I'm starting to see where the square root of 3 comes from. Of course, for the other term, I don't think we really need to remark too much. X squared plus 1, we pretty obviously have x squared plus 1 equals 0, implies x equals plus or minus I. I mean, I think most of us are pretty familiar with complex numbers at this point. So now the last step to do in order to see that this in fact is the splitting field, it's a little bit of a trivial step, but it's to take these four roots and just figure out what is the smallest field extension of Q that contains all these things. Well, Q already contains this, and so I don't need that. Here I need to adjoin a square root of 3. Properly speaking, one should show that the square root of 3 is not in Q, but this is a classical fact. I mean, I think most of us are familiar with the proof that kind of starts like this, right? And then reasons that, this thing is not reduced, this classic proof by contradiction. And then, of course, there are no imaginary numbers in Q, and so plus or minus I is necessary to adjoin as well. Okay, I think that more or less handles this problem. I think the problem that's a little bit more interesting is to look at problem 2. This is a little bit of a warm-up, I guess. Problem 2 gives us two fields, namely x squared minus 3 and x squared minus 2x minus 2, which we just looked at, and asks us to prove that they are both irreducible and in particular, they have the same root field. And the reason that this example is interesting is because what it shows us is that we can have different polynomials with the same root field. In other words, the root field is not an invariant all by itself. That should make some amount of sense in light of this example because the square root of 3 is the part that determines the root field. If I was instead dealing with 2 plus or minus square root of 3 or 5 plus or minus square root of 3, all those things would still be in Q, right? So we would still have the same square root of 3 contribution to the root field. And in fact, that's exactly what happens here because, well, we calculated the roots of that thing already, or rather the second thing. Maybe we'll call these guys 1 and 2. the roots of 1 are obviously, sorry, that's not a minus sign, plus or minus the square root of 3. And the roots of this guy are 1 plus or minus the square root of 3. And so while this may not be counterintuitive, I think this is relatively straightforward. It's still nevertheless an important core property. So I figured I would do this one to sort of start calibrating our intuition, our expectations a little bit. You guys are going to continue this line of discussion in the homework, looking at more problems from this section and trying to continue to fine tune your intuition for what these root fields look like, at least over Q. One remark that I want to make is that in other references, like if you feel a little bit stuck and you're looking around on the internet, Pinter calls these things root fields, and I've been calling them root fields, but they're often called splitting fields in other references. And so if that terminology helps you, we'll record that for posterity. You may find it useful in your internet search to use these keywords. Okay, the next example I want to show, we'll do this in a separate video. I want to look at characteristic P as well. So here we've done characteristic 0. Now we hold that thought. I'll show you guys some stuff about characteristic P, and I'll see you in just a sec.